So the next section is 1.2, properties of lattices. I want to start with some preliminaries. I already mentioned these a little bit, but I'd like to make sure that it's clear. So we define the following things. Z is the set of integers, so that would be ... -2, -1, 0, etc. N is the dimension of a lattice, so that Z sup n will be the set of all integer vectors in n dimensions. Rn is the Euclidean n-dimensional space. We're often drawing pictures in R2. X is a vector in boldface, so x1, x2, ... up to xn. We have usual vector addition, nothing surprising, x plus y. And then this double bar represents the squared Euclidean distance. Again, this is very simple, so we just have vector addition. Xn plus yn. That's very familiar. The squared Euclidean distance is denoted as x minus y, these are vectors, is equal to the sum on I is from 1 up to n of xi minus yi quantity squared. So this is very familiar and basic, but I'm writing it to emphasize one point, which is we almost always deal with squared distances rather than distances, because if you take the square root, then it introduces this irrational element and it becomes very messy. And with lattices, it's almost always the case that squared distances are integers. So this is much more convenient. Oh, this one? Well, this is just notation. This is the 2 norm. Sometimes people write it like that. Okay, so the other preliminary is algebraic structures. So we're interested in groups, rings, and fields. Who has seen groups, rings, or fields before in a class? We cover them in the coding theory class, but yes? No? Do you know what a group is? You forgot. Okay, good. I'm glad you're taking the class. Okay, so let's review the basic algebraic structures. This is the simple, non-technical definition. So a group is a place where you can add and subtract. Now, when we say place, we actually mean a set. It's more technical. A ring is a place where you can add, subtract, and multiply. And a field is a place where you can add, subtract, multiply, and divide. Okay, so let A be a set. Let plus and times be binary operations. And we'll let little a, little b, and little c be elements of the set big A. Now, the operations plus and times are in quotes because these may not be the usual plus and times that you're familiar with. And we'll define them specifically for that set. Closure under addition. That is, A plus B is an element of A for all A and B. So that simply means if you add any 2 elements, they're still going to be in the set. Associativity. That means A plus parentheses B plus C is equal to A plus B parentheses plus C for all A, B, and C. 3, we need an identity. That is 0 plus A is equal to A for all A. So this is consistent with your usual sense of adding 0 to anything. You get the thing back again. And then finally, invertibility. we have A plus minus A is equal to 0 for all A. That is to say, for any element A, there's an inverse such that if you add it to itself, if you add the inverse to itself, you get 0 back again. All right, if the set and the operation satisfy these properties, then we say it forms a group. An abelian group is a special type of group that has an additional property, 5. It commutes. That is, A plus B is equal to B plus A for all A and B. And then A with plus and times forms a ring if in addition you have associativity for multiplication, multiplicative identity, distributive property, A with plus and times forms a field. A field is a place where you can add, subtract, divide, and multiply. So if you get all the way down to multiply and divide, so if you get all the way down to dividing, then you have a field. I'm going to list some properties of lattices. The first one is that the origin, the all zeros vector, is always a lattice point. So because the lattice consists of integral combinations of the vectors, generator vectors, and there's no limit on the number of integers, that means the lattice is similarly infinite. There's no limit on the size of the lattice. If x and y are elements of the lattice, then x plus y is also an element of the lattice. Suppose that x is equal to g times b and y is equal to g times c, where b and c are some integer vectors. Then x plus y is equal to g times b plus c. So since b is an integer vector and c is an integer vector, the sum of two integer vectors is still an integer vector. Therefore, x plus y must be a lattice point. So this linearity property is very important and interesting. So you could state it a slightly different way. So what it means, if you stand at the origin of your lattice and look at all of your neighboring lattice points, you can see your neighbors. But then if you went and stepped at some other lattice point and looked around at all of your neighbors, you would see the same thing. That is, if you move from lattice point to lattice point, what's around you is the same. And the lattice is infinite, so you could keep going on until the end of infinity. Okay, so then the fourth property is that the lattice lambda forms an abelian group under addition. We have closure. That was given by property 3. We said that if you take the sum of any two lattice points, it will be in the lattice. The sum will be in the lattice, therefore we have closure. We have an additive identity. And that's 0, which we stated here. We have inverses. Minus x. So just take the inverse component-wise of the vector. You have its inverse. So of course, x plus minus x is equal to 0. And then it also commutes. And it's associative, D and E. So addition of lattice points is commutative and it's associative. Therefore, since we have these 5 properties, lambda forms an abelian group.